Hey everybody, this is Dr. Jacobs, and this week we are going to be combining everything that we've done so far this semester into the hypothesis testing steps. So you are officially out of statistics bootcamp, and we're going to use all this information so that we can start learning to solve problems using data. All right, let's get started. All right, so we have some unit learning objectives. Remember, these are the things that I want you to be able to do by the time you get to the end of this unit. And so since this is these are online videos, you're going to really have to test yourself and keep yourself accountable that you're able to do these things. If you're not able to do them, please reach out and ask questions. Come to my office hours so that I can give you some extra help. But it's really important, as you know by now, I really want you to understand and be able to think critically about the things we're doing in this class. All right, so by the end of this unit, I want you to be able to explain the hypothesis testing steps and its related terminology in your own words. I want you to be able to describe what goes into determining the appropriate statistical analysis for a research question. I want you to be able to classify hypotheses as research or null hypotheses and whether they are written directionally or non-directionally. I want you to be able to communicate how to check for the four most common assumptions and what it means if a statistical analysis is robust to the violation of an assumption. And these are a lot of fancy words right now. We will work through them. Like I said, from the beginning of this class, this is a language class more so than a mathematics course. And so we'll learn what this terminology means. And then when you read that, you'll know what this whole unit learning objective actually means. I want you to be able to explain the role of test statistics in the hypothesis testing steps. I want you to be able to discuss the role of critical values in the hypothesis testing steps. I want you to describe how to make a decision during the hypothesis testing steps. I want you to be able to distinguish between type 1 and type 2 errors. I want you to be able to also explain what is gained from conducting follow-up analyses. So these are a lot of different things that you're going to have to do. Something that's interesting about this unit is that we will actually use this as a template for every single week after this. Sometimes students are really nervous because there's a lot of information that we're learning in this unit, and that is okay. That is normal to feel a little overwhelmed. But this week, our primary goal is to learn the process that we're going to reuse over and over and over again with each of the different inferential statistics that I'm going to teach you. All right, so I like to use a metaphor for this because sometimes students are like, wait, were you doing the same thing over and over again? We absolutely are. So the metaphor I like to use for the hypothesis testing steps is making cheesecakes. So one of the things I like to do is bake when I get stressed out. It actually helps me kind of focus and get back into what I'm doing. And so sometimes I have little things that I get obsessed with making for a while. Once it was cheesecakes. So let's make some cheesecakes. So for our metaphor, our hypothesis testing steps, we're going to say is our recipe for making cheesecakes. And so there is a similar process that you make no matter what kind of cheesecake you're going to have. You have your cream cheese and you have your powdered sugar, and you're going to cream them together. And if you don't do that, that causes problems later on, but you're going to cream those together. You're going to add eggs one at a time. You're not going to overbeat the eggs into the cheesecake mixture. You're going to create some sort of crust, right? So you're going to grind up whatever you're using to make that crust, whether it's Oreos or graham crackers or whatever you're going to use, vanilla wafers. And then when you get the filling done, you put it into the pan with the crust. Then you're going to create this water bath thing. So sometimes you get like this big roasting pan, and you're going to put tinfoil around the spring pan that the cheesecake's in. You're going to set that cheesecake pan that has the foil around it into the big roasting pan. And then you're going to fill up water around it about halfway. And because when you use a water bath, when you're making cheesecakes, it's what makes it cook evenly. And it also makes it a lot more creamy when you're done doing that. So these steps are pretty much all the same, no matter what cheesecake you're doing. The steps are pretty much the same. What is different, however, are the ingredients, right? And so with our metaphor, we're going to learn about something called parametric assumptions. And in this metaphor, these are going to be the ingredients. So if you're making a traditional cheesecake, that's pretty simple. You follow the steps where you're doing the cream cheese in the sugar, and you're making sure that they're creamed in really good together, and the eggs one at a time, add the vanilla or whatever, and then you bake it, and then you can top it with like cherries or something like that. But there's different ingredients for that cheesecake than if you're making a double chocolate cheesecake, where you might have an Oreo crust, you might melt some semi-sweet chocolate chips and beat it into the cheesecake batter. You might actually put little Oreos or chocolate chips on top, but the steps are going to be the same. The thing that's different are these ingredients, right? If you're doing a dulce de leche cheesecake, you might do like a basic regular vanilla cheesecake, but instead have like caramel swirled in so that it cuts through the whole cheesecake. And maybe you might use a vanilla wafer crust for that one. So when we're looking at this week, we're learning the basic recipe for the hypothesis testing steps. Every week after this, we will learn one statistical analysis a week for the rest of the semester. And so what will change sometimes are these parametric assumptions or our ingredients. So if I gave a more formal definition, our parametric assumptions are the conditions that our data set have to meet so that we can do that statistical analysis, okay? And so when we're doing this, anytime that we're doing these hypothesis testing steps, the reason why we are is we're trying to answer some research questions. And so typically writing research questions would be something that you would learn in some sort of research methods course or research design and analysis. The way that our university has this set up is that we have statistics as a prerequisite to the research methods course. So if you're going on and in the fall, you'll be in the research methods course, you're going to want to keep these things because you'll be writing your own research questions that you'll answer using the statistical analyses that you're learning in this class. All right. So this is kind of a funny definition, but it's true. So a research question is the question that you're asking as a researcher. Okay. And so, for example, if I wanted to know if the suicide warning signs predict suicide attempts, what would my research question be? So don't write it in the comments. Think about this. And then we're doing Dora the Explorer again, where we're going to just answer it out loud. So if we wanted to know if the suicide warning signs predict suicide attempts, what would the research question be? It would be the following. Do the suicide warning signs predict a suicide attempt? And so with that, you see that it's answered with a yes or no. Most of the time when we're writing research questions, it'll be a yes or no type question because what we'll do is we'll have a data set and we can literally answer this question through using these different types of statistical analyses that I'm going to teach you for the rest of the semester. So the purpose of our hypothesis testing steps or these process is to answer these research questions. And that's really exciting for me. I think as humans, we are naturally curious and we are natural little scientists. And at some point, we lose some of that. But with statistics, it's really exciting because no matter what field you're in, you can use this to improve whatever practice you're doing. So if you're going to be a therapist, you might have a research question. Does this type of therapy reduce depression, right? That's really important information to know. If you are in athletic training, some sort of like kinesiology type field, you might want to know, does this type of intervention increase VO2 max? Right. And what you can do is design a study to test this research question and then use the statistics that we're learning in this class to be able to answer those research questions, which then can inform your practice. Even any field, like literally grocery stores do this. The reason why they rearrange grocery stores is it keeps you in the store longer, which makes you buy more things. Right. So they've used scientists for this. Within music, they know that if you have an introduction to a song that's over 20 seconds, most people aren't going to listen to it, right? So most of the Billboard Top 100 songs have introductions that are less than 20 seconds long. And all of this comes from data, from asking research questions, and then using statistical analyses to see what the answer to that research question is. So again, a research question is the question you ask as a researcher. That makes it more clear, right? But really, that's what it is. It's literally you come up with a question and you test to see what the answer is. All right. So the hypothesis testing process or the hypothesis testing steps are the following. Step one, you got to determine which statistical analysis to use. You don't know how to do that yet, but we'll get there. And we're going to go through these steps. You should actually memorize these steps in order because we're going to use the same format to go through each of the analyses that I'm going to teach you each week. So step one is determine which statistical analysis to use. Step 2 is write the research and null hypotheses. Step 3 is check the assumptions. That's to make sure you have the ingredients to do the analysis that you're trying to do. Step 4, we're going to calculate something called the test statistic. This is a number that we get from plugging our information from our data set into a formula that will help us make a decision about what we think the right answer is. Step 5, then we're going to find a critical value. We'll talk about what that means in a little bit. Step 6, you're going to make a decision. And step 7, you'll conduct any relevant follow-up analyses. All right, so let's go ahead and get started with these. So our first step for this would be to determine which statistical analysis to use. And there's many things that go into trying to figure out which statistical analysis you're going to use. Right now, we're not learning any analyses. We're just learning this process that we're going to be using. But the process for determining which one we're going to use is pretty much the same. One of the big overall goals for this class, if you remember back to our course learning objectives, not just the unit ones, but the overall course, I want you to be able to determine what statistical analysis to use given certain circumstances. And so we'll start learning how to do that now. So the first thing you have to ask yourself, what is the goal for your analysis? There's different types of things that you can do. In this class, we're mainly going to look at, are there significant differences between groups? So that's one type of goal. Is there a relationship between variables? Or another one might be, does one variable predict the outcome on another variable? So differences, significant differences, relationship, and prediction are some types of goals that we might have for analysis. What level of measurement are the variables? Specifically, a lot of times we'll be looking at the dependent variable and seeing if it's on an interval or ratio level of measurement. Data that is on an interval or ratio level of measurement are also known as what? If you said scale, you're correct. Step 3, how many samples are being tested or how many groups are being tested? Specifically samples, because we're going to learn an analysis later called a one sample z-test. So it's using one sample, but we'll talk about that a little bit later. Another question you got to ask yourself was between groups, within group, or match group design used? Okay, so we're going to learn a bunch of different types of analyses. You don't necessarily need to know when to use each of these yet, but these are ones that we'll either learn how to do or we'll talk about within class. So a one sample z-test is one we'll learn to do. One sample t-test, an independent samples t-test, a dependent samples t-test, a one-way analysis of variance, also known as an ANOVA. We'll learn about a factorial ANOVA, but we won't actually calculate that one. We'll learn about Pearson product moment correlations. We'll learn about linear regression. And if we have time, we'll learn about the chi-square for goodness of fit. And so these are different types of statistical analyses. Each week, we will learn one of these and take them through these hypothesis testing steps that I'm teaching you. All right, so step 2 of the hypothesis testing steps is writing the research and null hypotheses. So whenever we have a research question, there's only 2 possible answers to this research question. One answer, it could be the research hypothesis, or the answer is the null hypothesis. These are our only 2 possible answers to a research question. When we write these, we'll learn to write them both in symbols, and we'll also write them into words. These 2 hypotheses are complete opposite explanations of one another. So they cover every single possible outcome that we could get. Some people, really get nervous about statistics when taking it, but I think it's really kind of neat because there is a right and wrong answer. A lot of classes you can get away with kind of BSing your way through different things, but with statistics, we actually have a firm and correct answer, which to me, I like that. I take comfort in that and being able to know if I'm right or wrong. And so some students get nervous about that, but that's why I have office hours that you can come into. And if those times don't work, then we can try to find a time that works for us. Okay, so again, we have our research hypothesis, we have our null hypothesis. And when we write our research and null hypotheses, either we can write them directionally or we can write them non-directionally. Okay, but our research and our null hypotheses come in pairs. So if you write your research hypothesis directionally, you also have to write your null hypothesis directionally. Or if you write your research hypothesis non-directionally, you also have to write your null hypothesis non-directionally. Okay, And I'm going to repeat this because it's something that students sometimes struggle with. If you write one directionally, you also have to write the other one the same way. Okay. And we'll get into more why this is as we move along into this unit. A lot of times we determine directionality based off of reading previous research. I mentioned this before, statistics fits within research design, right? So research design is a different class, and at this university, it comes after stats, but that's where you design your study, you write your research question, and then statistics is used as a part of that process to answer whatever research question you have. As part of whenever you do research of some sort, you're always going to start by reading what has happened or what has been done in the past. You're going to review peer-reviewed studies to see, okay, oh, they've already studied this, they've studied that. And then you're going to come up with an idea that hasn't been done before, or you're going to tweak a previous study that's already been done, unless you're doing some sort of direct replication where you're trying to see if you come up with the same result as a different scientist. And so when we write our hypotheses directionally, a lot of times we have an idea of, if we're comparing two groups and we want to see if one is more than another group, if we have an idea which group is going to be more, we're going to write our hypotheses directionally. If we're doing some sort of kind of exploratory thing, we don't know which group would be more, then we'd write those hypotheses non-directionally. However, usually we want to write our hypotheses directionally if we can, and we'll get into why in a little bit. For now, just trust me on this. But if you can write your hypotheses directionally and you have an idea which one will be better, that's what you want to do. Okay, so for example, if I am a pharmaceutical company and I want to see if my insulin medication reduces blood sugar in patients who have diabetes, I have an idea that I think the people taking the medication will have significantly less blood sugar levels than people who take a placebo, right? So if I have an idea which group will be higher or lower, you're going to want to write these hypotheses directionally if you can. Okay, so again, we can write our hypotheses two ways. If we write our hypotheses non-directionally, we think there might be a difference. We just don't know where the direction of that difference is. If we write our hypotheses directionally, this is when we have an idea if a group will be either larger than another group or if a group will be smaller than the other group. So again, if you write your research hypothesis directionally, you also write your null hypothesis directionally. But if you write your research hypothesis non-directionally, then guess what? You're also going to write your null hypothesis non-directionally as well. They come in pairs. What you do to one, you do to the other one as well. Okay, so directional versus non-directional hypotheses. Non-directional hypotheses, when we write our hypotheses non-directionally, when we're running the statistical analysis, we say that we're doing a two-tailed test. This is something you're going to want to keep in mind. As we move through this material, we actually will end up drawing out a normal curve. And if we have a non-directional hypothesis, we're actually going to put two tails on our normal curve. And so here, this is just where we're saying there's significant differences between groups. Directional hypotheses then uses a one-tailed test. So when we draw our normal curve for one-tailed tests, we'll only have one tail. And this is typically where we say that one group's higher than another group. Okay. Again, the idea about the direction of our hypothesis usually comes from the research. So directional hypotheses are used for one-tailed tests. You have a guess to which group will have a higher score. So for example, the students in my class will have a statistically significant higher mean ACT score than the national mean ACT score. Non-directional, again, is used for two-tailed test. This is where you don't have an idea which group will have the higher score. Here you just indicate that there's some sort of difference. Example, there's a significant difference between the national mean ACT score and the class mean ACT score. All right, so let's get into how this might look. This will actually change depending on what statistical analysis you're using. This is just to use as a primer so that we get familiar with what we need to do. Okay. So if I had a non-directional example, you might want to know if people lose significantly different amounts of weight between the keto and Whole30 diets, but you're not sure which diet would be more effective at helping people drop weight in the first month. If we don't know which group, then we're going to write our hypotheses non-directionally, okay? So you would take a sample of participants, let's say our sample size equaled 100, and we randomly assigned our participants to be either on the keto diet or the Whole30 diet for 1 month. This means that we would have different participants in the keto condition from the participants that are in the Whole30 diet condition. In other words, we're using a between group design. So then we would collect data on how much weight each of the participants lost during that 1 month period. Okay. So what would our research question be? And I can go back so you can read that. You can pause this. What would our research question be for this? Research question: are there significant differences in the amount of weight that people lose in the first month on the keto or Whole30 diets? So then we would need to write out our hypotheses. Once we have our research question, we would want to write out our hypotheses. Typically, it's easier to write our hypotheses out in symbols first and then translate those symbols into words. All right, so H1 is going to be our symbol for our first research hypothesis. So the letter H stands for hypothesis. So go ahead and write that on your handy dandy symbol sheet right now. So you're going to put H, italicize H. The sub 1 there is just saying it's our first research hypothesis. For most of the analyses I'm going to teach you in this class, there'll only be one research hypothesis. However, when we get to talking about some later types of analyses that are a little bit harder, there may be more than one. Sometimes you'll see the symbol H sub A used as research hypothesis, because what that actually stands for is alternative hypothesis, but that is just another way or another name that people refer to for the research hypothesis. So go ahead and put that symbol in your symbol sheet too. So H sub A means alternative hypothesis. Okay, so here we're saying there is a statistically significant difference. And when we're talking about research hypotheses, usually this is the one that researchers want to be the most accurate explanation for their research question. Okay. So then we also have our null hypothesis. Our symbol for null hypothesis is H sub 0. H stands for hypothesis. The sub 0 that just indicates that this is the null hypothesis. Because if we look at the word null, that actually means 0 or lack of. So this symbol can be quite intuitive if we look at it and then try to interpret it. I think sometimes students get super nervous about the content, but if you just look at it and really try to understand what it's saying or try to read it like language, it can be a lot easier on yourself when doing that. And typically when we have a null hypothesis, we're saying there is not a statistically significant difference. Usually this is the one that researchers do not want to be the most accurate explanation for their data or what's going on with their data set. Okay, so research hypotheses in symbols and in words. If I was going to convert this into symbols for our example that we're doing, we have H sub 1, which means it's the research hypothesis. Then we're going to put a colon there that says, here comes our research hypothesis. We'll see with this analysis that we're comparing the means of the two groups, right? So we have X bar, which represents sample mean, sub keto. So we're saying the mean amount of weight loss for the keto group. And then we have the does not equal because we just said we think there's a significant difference. And then we have the mean of the Whole30 group. So if we wanted to translate those symbols into words, we have the research hypothesis. The mean amount of weight people lost on the keto diet in the first month is significantly different than the mean amount of weight people lost on the Whole30 diet in the first month. That's really wordy, and I actually made it a little bit more wordy than it needed to be, mostly so that you could see the format that we're doing. When you write your research null hypotheses, they're likely to be slightly different ways to word it, so they may not be the same as all your peers. It just has to cover what we're saying, and here we're saying they're not equal to each other, right? And so there's different ways that you could say that. So then we also need to write our null hypothesis symbols and words because we wrote our research hypothesis non-directionally, we have to do the same thing with our null hypothesis. So here we see we have H sub 0, which tells us null hypothesis. We put that colon there to indicate that we're getting ready to tell you our null hypothesis. And the thing that you'll notice, we kept our groups in the same order, which is something I advise always doing. We have the same groups. We have the mean of the keto group, weight loss from the keto group. We also have the mean of the weight loss in the Whole30 group. But the major difference here is instead of having the do not equal sign, when we have the null hypothesis, we're saying that the groups are equal. So then we can translate that into words. Null hypothesis: the mean amount of weight people lost on the keto diet in the first month is not significantly different than the mean amount of weight people lost on the Whole30 diet in the first month. So tying it all together, we have our research question: are there significant differences in the amount of weight that people lose in the first month on the keto or Whole30 diets? Our research hypothesis was that the mean amount of weight people lost on the keto diet in the first month is significantly different than the mean amount of weight people lost on the Whole30 diet in the first month. And our null hypothesis is opposite of that research hypothesis, right? So null hypothesis: the mean amount of weight people lost on the keto diet in the first month is not significantly different than the mean amount of weight people lost on a Whole30 diet in the first month. And so what we see here is we have our research question, and then we have two possible answers. Only one of these answers can be right. Only one. Either the research hypothesis or the null hypothesis will be correct. All right, so then we can also write our hypotheses directionally. You will only do one or the other. You'll either write your hypotheses, your research and null hypotheses non-directionally, or you will write them directionally. You do not do both. And so sometimes students get confused, especially in this first lecture where I'm teaching the hypothesis testing steps, because they think they have to do both. And that's not true. You will either write them non-directionally or directionally. But the way that you write one, you will also write the other. All right, so a directional example. Drinking my water here. Okay, so for example, I expect that students after they read my entire stats textbook that I'm writing, they should know more about statistics than before they read it. If they don't learn more, or they have the same amount of knowledge, I failed at my job of writing this book. Okay, so to do this, I might set up a study where I randomly select a sample of people who purchased my book so that I could test their statistical knowledge using a pre-test before they read it, and then test them again after they read it. This means I would have the same participants in the pre-test condition and the post-test condition. So in other words, out of those 3 different types of research design we learned during week 1, I'm using a within group design. All right, so what would our research question be? And we can go back to this. I'll give you a minute. You could actually pause me. I don't have to give you a minute. You can give yourself a minute. So pause me right now and then try to develop your research question. All right, so our research question is: do people who read this textbook know more about statistics after reading the entire book than before they read it? So here you'll see when we're writing our hypotheses directionally, that when we look at a research question, we're trying to see if one group has more, right? We think that people who, after people have read it, they should know more, right? We're putting a direction on what we're trying to do here. So when we write our research hypotheses in symbols and words, we're going to use a direction. And it's a little bit more difficult to write our research hypotheses directionally, just because it can be a little bit confusing. But once we get a little bit more practice, like I said, we're going to be doing these steps over and over and over again. Then it'll become just automatic for us. So we have H sub 1. We know that's a symbol for our first research hypothesis. We put a colon then to say that our research hypothesis is coming. Here we're comparing the mean of our post-test group's knowledge, and we're saying that we think that's going to be significantly greater than the mean amount of statistics knowledge that people had before reading the book. So if we want to write that out into words, we would write research hypothesis: the mean amount of statistics knowledge people know after reading this textbook is significantly larger than the mean amount of statistics knowledge people knew before reading the textbook. So like we said a couple slides ago, if you can write your hypotheses directionally, that's more advantageous for you. And we'll learn about a little bit more why it's more advantageous a little bit later. Okay, so then once we write our research hypothesis, we need to write our null hypothesis in symbols and words as well. So we have H sub 0, that is the symbol for our null hypothesis. Then we're going to put a colon to say, here comes our null hypothesis. And here we'll see it's a little bit more complicated when we write our hypotheses directionally, because in our research hypothesis, we said that the post-test was significantly greater than. When we get to our null hypothesis, we'll have that the mean amount of knowledge that the post group has, the post-test is significantly less than or equal to the amount of knowledge that people had before they read the book. So if this ends up being the best explanation for what's going on with our data set, that means I failed at my job, which is kind of scary. So null hypothesis, the mean amount of statistics knowledge people knew after reading this textbook is significantly less than or equal to the mean amount of statistics knowledge people knew before reading this textbook. Okay, so if we tie it all together, we have a research question. Do the people who read this textbook know more about statistics after reading the entire book than before they read it? Our research hypothesis answer is saying, basically, yes, they do. Our null hypothesis then is saying, no, they either know the same amount or they even know less. And as the person who wrote the book, I don't want that to be the explanation for what's going on. So pro tips, when you're writing your hypotheses, write your hypotheses in symbols first and then put them into words. I would actually write both my research and null hypotheses in symbols first and then translate them into words second. And then when doing this, I always write my research hypothesis first, then I write my null hypothesis, because the research hypothesis is the one that we're actually interested in as researchers. Another tip is to keep your groups in the same order when writing your hypotheses. This really comes in handy when we're writing our hypotheses directionally as well. Again, if you write your research hypothesis non-directionally, you also have to do that with your null hypothesis. Remember, whatever your research hypothesis does not cover, your null hypothesis needs to cover. One of these will be what you determine to be the answer to your research question. All right, so that moves us on to step 3. So step 1, we had to determine which statistical analysis we were doing. Step 2, we wanted to write our hypotheses. Step 3, we're going to check our assumptions. Okay, so again, if these steps that we're doing is our recipe, our assumptions are the ingredients to our statistical analysis. These ones will change depending on what analysis we're doing during the week. So sometimes in baking, you might be missing an ingredient. I don't know how many of you bake, but if you're making a cake and you do not have oil, that's actually not the end of the world. If you don't have oil, you can actually have different things to substitute. What are some things you think you can substitute for oil in a cake when baking? So there's different things you can use. You can actually use applesauce. And sometimes people actually use applesauce instead of oil anyway, because it cuts the amount of calories that are going into the cake that they're making. It's a little bit healthier. And you can substitute it and it doesn't really change the texture. I mean, there's a little subtle change, but it's a pretty good substitution if you're out of oil. So you can do that. But if you're making some sort of flour-based cake, if you don't have flour, you might have trouble finding a substitute for that. So keep that in your head, because when we're checking these assumptions, sometimes if we violate the assumption or we don't have the particular ingredient that we need, sometimes we have different things that we can substitute in place for it. And that means we can still run our analysis anyway, even if we don't meet all those original assumptions. So the word robust is kind of what the word is if we can use one of these substitutions, right? So robust means that you can still run the analysis if you violate an assumption, given that you follow certain conditions. And we'll learn what those are when we learn individual different types of statistical analyses. So there are 4 common assumptions that we'll see very frequently throughout the rest of the semester. One is that our dependent variable is measured on a scale. What's a scale again? A scale is data that's on an interval or ratio level of measurement. So from very first week of this class, I was saying that's really, really important to learn these levels of measurement. And this is why. Actually, we have to determine what kind of analysis we can do based on what level of measurement our dependent variable is. So for most of the analyses that I'm going to teach you, if our DV is not on a scale, then you can't do it. There are other analyses called non-parametric analyses that I won't be teaching you, but you could take an entire class on non-parametrics that if your DV is on ordinal level of measurement, that you might be able to use those type of analyses instead. Another common parametric analysis or a parametric assumption that we have is that the population where we got the sample from was normally distributed. In other words, that if we put our sample data onto a histogram, it would follow the normal curve if it came from a population that had normally distributed data. Another common parametric assumption is that we randomly selected our sample from the population that we're studying. And then a fourth common parametric assumption is that our dependent variable is free of significant outliers. So parametric versus non-parametric analyses. So we remember that with statistics, we're interested in studying quantitative data or data that's represented by numbers. In statistics, there's two major branches. We have descriptive statistics, which are numbers that describe our data set in one or a few numbers. And then we have inferential statistics. We're getting ready to move into the inferential statistics where we take a sample from a population to try to make guesses about what's going on in the overall population together. Inferential statistics can actually be broken down then into parametric analyses and non-parametric analyses as well. So parametric analyses assume that the data from the population of interest is normally distributed, or it actually follows kind of that normal curve shape that we learned about. Non-parametric analyses refrain from making assumptions about the shape of our distributions. What's a distribution again? A distribution is how frequently each value occurs in the data set. And we learn different ways to display a distribution. We learn those frequency distribution tables. We also learn how to build a histogram. Usually parametric analyses have more assumptions than non-parametric analyses. But just trust me for now, if you can use a parametric analysis, you actually want to do that. And in this class, we're going to be basically learning all parametric analyses. You could take an entire class on non-parametrics as well if you wanted. Step 4, we're going to calculate the test statistic. The way that we calculate a test statistic depends on which analysis we're conducting. Each statistical analysis will have a different formula, and you'll use your data set to plug into this formula to calculate this test statistic that will represent your data set. So the test statistic refers to the specific statistic you are testing in order to answer your research question. Again, the test statistics will have different formulas and are used to test different types of research questions. So for example, we'll learn a one sample z-test that uses the z-test statistic. We'll learn a couple different types of t-tests, and so that will be represented by t. We'll learn ANOVAs, which will be represented by the f-test statistic, and we'll have a formula associated with that. Lowercase italicized r represents correlation, and chi-square represents the chi-square. Step 5, then, we're going to find critical values. Okay, so once we've tested our assumptions, and once we've calculated our test statistic, we're going to set our alpha level and find our corresponding critical values. So to do this, let's do a little bit of an example with some sampling, okay? So if I wanted to find out if high schoolers in states that mandate abstinence only or comprehensive sex education programs engage in riskier sexual behaviors, my research question would be as follows. Do high schoolers in states requiring abstinence only sex education have significantly different levels of risky sexual behaviors than high schoolers in states requiring comprehensive sex ed? How would we study this? What would we do? Pause me and think about it for a minute. We would have to take a sample, right? So we'd take a sample, and we would take a sample of high schoolers in states that mandate abstinence only education versus states that have or mandate comprehensive sex education programs, so that we could try to answer this research question. So the problem is anytime that we take a sample, there is a chance that we don't actually get a sample that represents the population. And so the difference between the results we get with our sample and how results actually occur in the population is called sampling error. Because of the sampling error and other types of error, remember we learned about measurement error, we learned about random error so far in this class, is that we can't just compare the numbers between the different samples to see if there's a difference. Like we can't just look at them. We actually have to see if those differences are large enough that the significant difference or the difference didn't happen because of the error that's incorporated in our scores, or because we took a sample, or because of random error. And so that's one reason that we need statistics. So when we're doing this, there's only two decisions that we can make with the hypothesis testing steps. We can either, one, reject our null hypothesis, or two, we can retain the null hypothesis. When we're making our decisions with this, it's always with relation back to our null hypothesis. So when we reject the null hypothesis, the data does not support the null hypothesis as the best explanation of what's going on with the population. When we retain the null hypothesis, then we actually think the null hypothesis is the best explanation about what's going on with the population with the information that we have from our sample. We want to, typically when making a decision, we want to be able to reject that null hypothesis. But to make our decisions with our hypothesis, we will compare that test statistic value that we have to the critical value that we find in this step that we're doing right now. So even with statistics, there can be errors. So even once we come to a decision, which would be the next step, even when we get to that, there'll be something called type 1 and type 2 errors that are possibilities. So if we get a type 1 error, and we actually won't know that we have a type 1 error from just doing this analysis, this is if we reject the null hypothesis when the null hypothesis was actually true. Okay. Type 2 error then is we retain the null hypothesis when the null hypothesis was actually false. Okay, so type 1 error. Another name for this is an alpha error. And so when we're calculating our test statistic, there is a p-value that's associated with our test statistic. But we're actually not going to calculate those p-values because we're going to use critical values instead to compare our test statistic to. But you could use calculus and figure out what the probability is, or the p-value of making a type 1 error. Our alpha level is the cutoff that we're going to use to compare our p-value to. Instead, for this class, because we're doing everything by hand, we will use a critical value that's associated with our alpha level, and we have our test statistic that's connected to our p-value. So an example of a type 1 error is a COVID test saying that you have COVID when you actually don't. That would be a type 1 error, saying you have results when you don't. A type 2 error then is a beta error. And a beta error, so a beta is the probability of making a type 2 error with the results that we have. So example would be a pregnancy test saying that you're not pregnant when you actually are. So let's practice a little bit. Let's identify if this is a type 1 or type 2 error. If a rapid strep test comes back negative, but the patient actually does have strep, what would that be? Test yourself before moving on. It would be a type 2 error. So alpha level and p-value. The alpha level represents the level of risk we're willing to take that we will make a type 1 error when rejecting the null hypothesis with our data set. In other words, this is called our significance level. The most common alpha levels that we'll use are 0.05 and 0.01. For this class, we'll almost always use 0.05, and that's what we'll use unless I direct you to do otherwise with the things that we're doing for the class. So a related phenomenon, a p-value represents the probability that you will make a type 1 error. So this is that our test statistic does not represent the population. So when you conduct your test statistics, you want your p-value to be less than your alpha level. Okay. So in this class, like I said, we're actually not going to calculate those p-values. We're going to compare our test statistic to a critical value. The p-value is associated with your test statistic. Your alpha level is associated with your critical value. Okay, so your critical value is going to be your cutoff. Okay, so the critical value then is the value that your test statistic needs to go beyond for you to get statistically significant results. So more in depth, if our alpha level equals 0.05, then our critical value is the value that our test statistic equals, where you have 5% chance of making a type 1 error if you reject the null hypothesis with the data set that you have. So if your alpha level is 0.01, your critical value is the value that your test statistic would be, where if you have a 1% chance of making a type 1 error if you reject the null hypothesis with the data set that you have. Okay, so there's something called increasing the power of the test. Our goal, hopefully as researchers, we're hoping to reject our null hypothesis. This is because there is a bias within like publications or journals where they only typically publish significant results. There is a whole journal dedicated to non-significant results, but often as researchers, we're looking to reject our null hypothesis. So we can do something where we increase the power of our test, and that is where we have 1 minus beta. If you remember, beta is a probability of making a type 2 error, which is a type 2 error, if we remember, is where we don't reject our null because of what we see with our sample. But if we had the overall population, we should have rejected it. So the power of the test is 1 minus beta. So when we increase the power of the test, we're more likely to reject the null hypothesis if it's false. There's several ways to increase the power of the test. One is to use a one-tailed test. Remember, I said if we can write our hypotheses directionally, we want to. That's so that we can increase the power of the test. 2, using a parametric analysis. So earlier when I said, trust me, you want to use a parametric analysis if you can. That's so that we can increase the power of our test as well. Third one's increasing our sample size. So if we increase our sample size, we also increase the power of the test. Increasing our alpha level also increases the power of the test. Okay, so step 6, then we're going to make a decision. Remember, we have 2 different decisions we can make. We can retain our null hypothesis or we can reject our null hypothesis. We're going to use our critical value that we found in step 5 to differentiate between these 2 different regions. And so if we remember, our means in the middle, if we're doing a 1 sample z-test, we know that there's a z-score of 0 right in the middle of that normal curve. And so we want to compare our test statistic, and we'll actually put our test statistic somewhere on that line below our curve there and compare that to our critical value to see if we have statistically significant results. You're going to label your normal curve every time that we do it. You're going to label it with our critical value if we're doing a one-tailed test, or critical values. You'll have 2 if you have a non-directional test. You're also going to label the test statistic on there and our different regions, retain the null hypothesis or reject the null hypothesis, so that we can visualize the decision-making process. In this step, you will either reject or retain your null hypothesis. So 2-tailed test, this is what it would look like. And we'll get into more of how to do critical values and things when we move along in the lectures where we're actually doing different statistical analyses. So if you have a 2-tailed test, you're going to have 2 critical values. You're going to have a positive critical value. You also have a negative critical value. They'll actually be the same number, just one will be positive and one will be negative. We also have a 1-tailed test, and that's if you hypothesize. This drawing is if you hypothesize a negative test statistic, which makes sense because we then have our critical value on the left of our distribution here. If you hypothesize a positive test statistic, or you'll run a 1-tailed test and your critical value will be positive. Step 7 then is conduct follow-up analyses. There's different ones we'll learn. We'll learn something called effect size. And so just because we found significant results in step 6 doesn't mean that those results are meaningful. So we use effect size to try to see how big those differences are. So what do you remember? What happens if we increase our sample size? You said we increase the power of the test. You're absolutely correct. So that's one of the ways that we increase the power of the test, but you can actually increase your sample size so much that it's super easy to find significant differences. Okay. Something else that we can learn to calculate is confidence intervals. This gives us a range of values that the test statistic might fall, because we know that whenever we have any score, any obtained score, there's always the true score plus error. We don't know how much error is in that obtained score, but we know that it's there. So confidence intervals is actually a whole another different way that you can do the hypothesis testing steps, but we'll learn more about that later. I don't know if you've ever seen on TV, they used to have where they would do like political polls and say like, what is the approval rating of Mickey Mouse as president? And they'll give a number and they'll have like plus or minus 2%. They're actually giving you the confidence interval. They believe like if Mickey Mouse's approval rating as president was 50%, the plus or minus 2% would be the approval rating probably somewhere in there is between 48% and 52%. And that helps account for the error that are in scores. So that is all we have for this week. I know it's a lot of information. It'll get a lot easier once we have a little bit more to work with. So like next time we'll use an actual statistical analysis and we'll go through these hypothesis testing steps to answer research questions that will fit that analysis. And we'll keep doing it over and over again. So this is just a primer. A lot of times statistical stats books will not teach the process first, and we'll just go ahead and jump into inferential statistics. I do this so that we kind of have that repetition so that we know what the process is, and then we'll take that process and do different statistical analyses through that process week after week after week for the rest of the semester. If you have any questions, let me know. You can write comments or you can come into office hours, and I hope you have a great week.